Holzer's method is commonly used in MDOF system, but it assumes the structure behaves like a SDOF system. Let's say we apply method of section and randomly cut through a stiffness component. Now, we treat anything above this component a rigid body. The rigid body carries inertial force of all degree of freedoms above the stiffness component. Under equilibrium, the elastic restoring force in the affected spring element would equal to the summation of inertial forces. The displacement of the spring element would be the relative displacement between the degree of freedom just above and below it. Let displacement be a sine omega nt. The acceleration can be obtained by performing second-order derivative of x with respect to time. First, we substitute these expressions into the equation and simplify them by eliminating the common term sine omega nt. We then expand the right-hand side and move the force of stiffness involving displacement of I-1 degree of freedom to the opposite side. After that, we divide both sides with ki-1 to further simplify the equation. At this point, we rearrange the equation and obtain the final equation. Let's construct a table for Holzer's method for the 3DOF system we discussed in both iterative method and Rayleigh's principle. The story data should be written in top-down sequence when constructing the table. When using Holzer's method, we always consider the top story displacement as 1, since the mode shape of system is normalized. With an assumed natural frequency, we perform calculation until we know the base displacement. If that displacement is not 0, we need to repeat the process. For the first trial, let us assume the omega n squared as 0.3 k/m. Note that the summation of MA column should add up all MA terms of all the stories above and equal to the story we are attending. At the end of calculation for each row, we obtain the displacement of lower story, and this will be the term AI for the next row. The calculation continues, and we should notice that the base displacement for the first trial does not equal to 0. So, let's assume the omega n squared as 0.4 k/m instead. At the end of calculation, we notice the residual displacement at base level is moving towards 0 when we increase the value of omega n squared. This observation gives us the direction in deciding the next omega n squared. When the residual base displacement is more and acceptable, we may proceed with determining the natural frequency. Thank you for watching. If you find this video helpful, please share it with your friends. We'll see you guys soon. Goodbye.